Now let's talk about the next theorem. Say we call it say theorem 10, right? And it's a quite an important and famous theorem. It's called the De Morgan's theorem. Right? It says this, that if we take a plus b dash, this is equal to a dash dot b dash, and a b dash a dash plus b dash. Okay, this is our De Morgan's theorem. Now let's try to prove the De Morgan's theorem. Okay, to prove it, let us see that we go this way. Let us a plus b, okay, plus a dash b dash. Okay, let's see what it is. Okay, say equal to a plus a dash b, okay, plus b. What is this a plus a dash b? Okay, we can say that a plus a dash, right? A plus a dash, oh, a plus b dash plus b. This is equal to a plus b dash, because a plus a dash equal to 1, right? Plus b. If I take this, this is equal to a plus 1, and this is equal to 1, right? If a plus b plus a dash b dash equal to 1. Now let's see that a plus b a dash b dash, okay, this is equal to a dash b plus a b b dash. This is 0 b plus a 0, which is 0 plus 0, and that is equal to 0. And by complementarity theorem, right, by complementarity theorem, you see that if a plus b plus a dash b dash equal to 1 and a plus b dot a dash b dash equal to 0, immediately we have that a plus b dash is equal to a dash b dash by complementarity theorem, which we have already proved. Similarly, this we have proved, therefore the dual can also be proved in the similar line. Okay, therefore this is our De Morgan's theorem. Okay, and the proof I have given. Now let's a little bit retrace it back a little bit. That is this De Morgan's theorem we have, right? Then the law of absorption. Okay, that's quite an important theorem that we will have the occasions to use. Okay, extensively, right? Then the law of idempotence, right? Then the law of involution. Okay, this is a law of involution, right? Sorry, the theorem 1 has come earlier than this. This law of involution. Then the introductions of the identity elements are unique, and complements of an element is also unique. The identity elements are complements of each other. The complementarity theorem, right? The equality theorem, and the closure of the identity elements, together with all the axioms that we have told in the very beginning, gives us a, I should say, a framework by which we should be able to manipulate, okay, any system that conforms to this Boolean algebra, right? Now let us try to give one or two examples of it, okay? Say, let us take an example. Let us take B to be, right, that all the 8 factors of 30. Now say so long we had been doing on abstractions only. I am now trying to give an example in which I am defining what is my B, what is my plus, what is my dot, what is my complementation, and show that all the axioms itself turns out to be true, right? Okay, and all the theorems turns out to be true, right? What are the 8 factors of B? They are 1, 2, 3, 5, 6, 10, and 15, and 30. These are my 8 factors of 30, and that's my set B. Now let's see my LCM of any on these elements, okay, is essentially my plus operation. That means if I take 2 elements of it and take the LCM of it, that's my plus operations. Okay, right. Okay, and HCF is essentially the dot operation. Right. Now you see one thing, you can, if these be my operations, you can now see that LCM and HCF operations are closed. That means if I take any 2 of them, right, so 3 and 5, okay, LCM is 15, that is there, okay, and what is the HCF of it? 1, and that is also there. Therefore my therefore take any 2 elements, take the LCM of it or take the HCF of it, it should be within the set itself, that is closed. Okay. Now this also is very much true that LCM and HCF, these 2 operations, okay, are commutative and associative, right? 3 is LCM and HCF, okay, are distributive. Okay, let's take for example 3 dot 6 plus 10. Okay, 3 dot 6 plus 10. This is what? 6 plus 10. The HCF of 6 plus 10 is what? The 3 dot 30, and LCM of 3 and 30 is 3. Now distributive over, that means 3 dot 6 plus 3 dot 10. What is 3 dot 6? Huh? 3 dot 6 is 3, and what is 3 dot 10? 1. And what is that LCM of 3 and 1? 3. Therefore you see that this is 3 and this is 3, therefore the law of distribution, the distribution is distributive. Okay, right. Then let's see, what do you think is the identity elements? Identity elements. Acha. For plus it is what? 1. And for dot it is 30. Therefore I have the identity elements. Another thing what I will have to tell complements. Okay, that means the dash operations, complement operation, right? Now the complement operation, you get that by, say, if you have A, then complement A dash is equal to get by this, right? That means divide 30 by that element, you will get complement. For example, that if A equal to 10, then what is my A dash? 3. Okay. Now, in that case, A plus A dash should be what? Tell me. A plus A dash, LCM? 1. Okay. And A dot A dash, that means 0. Is it okay? Now, essentially what is happening that huh? I mean, what is your A plus A dash? Tell me. 30. And A dot A dash is? 1. A plus A dash is equal to 30. Okay. And A dot A dash is equal to 1. This is the identity element for plus, and this is the identity element for dot. That is exactly what I need. Is it okay? A plus A dash, if A equal to 10 and A dash equal to 3, A plus A dash equal to 30, right? This is the identity element for dot operations, and A dot A dash, this is equal to 1, and that is the identity element for your plus operation. Therefore, we have that identity elements, right? And you can see that if you take now all the theorems, you will find that all the theorems will hold good on this particular instantiation, okay, right? Particular examples of Boolean algebra. Is it okay that you can take all the theorems of it and you can try to see that's happening, because we have proved that all the axioms are holding. Okay. Now let's take another example of it. Okay, that say I take the set B to be a a void set, right? 1, 2 is a set, 3, 4, 5 is a set, 1, 2, 3, 4, 5 is right. Say this is my B. That means a set of subsets of 1, 2, 3, 4, 5. Okay. There's a void set I have taken, a subset 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let me name them as A, B, C, and D, right? And let's see that plus is essentially my union operation, represented by, say, this, okay, as you know, set union. Dot is my intersection, okay, right? And this dash operation is essentially my complementation operations, right? If you take this, right, and if you take the identity elements, okay, that means phi for union, right, and D, that means D for intersection, right, you will find that all the axioms are holding good, right, and this once more turns out to be, right, this example, an interpretation of a Boolean algebra. That means I defined plus as a union operation, dot as intersection operations, and complementation. This is my set, okay, that I have defined. My identity elements are this, and you'll find that all the axioms hold good immediately, and therefore all the theorems also will be holding good immediately, right? Now, with these two examples, the first one is an 8-valued examples. The set is having 8 values, okay, This has a 4-valued example, okay, the set having 4-valued, okay, 4-valued examples of Boolean algebra. Let's come to that the 2-valued Boolean algebra where B is equal to 0 and 1, right? We come to the 2-valued Boolean algebra, B equal to 0 and 1, and if B has to be 0 and 1, then they themselves are the identity elements, okay? And you have these two operations plus as defined by your axioms as well as by the theorems, that 0, 1, 0, 1, okay, this is 0, this is 1, 1, 1, and dot operation 0, 1, 0, 1, okay, this is 0, 0, 0, 1, right? This, with this plus operation defined as this, dot operation defined as this, okay, and 0 dash complement equal to 1, and 1 complement is equal to 0, that we have already, okay, established in the previous theorem. This is in fact what we call a switching algebra, okay. Therefore, what we will be interested in, right, in from now onwards, okay, is the switching algebra, which is basically a 2-valued Boolean algebra. And all the axioms that have been given and all the theorems that have been given, we shall be using extensively, okay, to maneuver the expressions written in switching algebra, in which we have only 2 values, 0 and 1, right? Now, therefore, let me stop here today. I shall be starting from the next class from the switching algebra. Okay.